Hello，乌鲁鲁。Yearn，不是。嗯，dismissed。Work。嗯。好。哦。Hello, Henry. Oh, still kinda. Oh. Hello. Hello. You have. Oh, okay. I can hear you now. Can you hear me? Oh, I can hear you. Oh, good.
Okay, good.
How's it going?
Good. We got a new computer.
You?
Yeah.
Me?
No,
Me? Huh?
Me.
Good. Okay. So what kind of computer is that?
Dell something.
Oh, okay. I also changed it to another computer today. So should be because it was frozen several times before. That obviously the memory thing is not enough. Just last time we talked about the cross product. We learned the dot product already. Do you still remember anything about the cross product?
No. Let me try to remember. Let's see.
I share my desktop with you anyway.
Oh, yeah, cross product is really weird.
Weird? Why is it weird?
Well, you need the 3 things only, and then you do like plus plus minus minus or something like that.
3 things only? What does that mean?
You can only be in like the 3 dimensions. So.
Yeah, essentially, yeah. Yeah, if like in the 4 dimension, we still think about, you know, the subspace of 3 dimension anyway. Yeah, essentially, it's only 3 dimensions. Yes.
Mm-hmm.
So it's essentially it's 2 vectors, then get another vector, right?
Mm-hmm.
That's what it is. So because the end result is another vector, so it has a direction as the length.
Mm-hmm.
The direction is something make the XYZ to be the right hand system, and the length is the area, the amount of the area of formed by those two vector. That's all about. So actually, it also has some kind of property. The end result is perpendicular to both of them. Yeah, that's it.
Mm-hmm.
The UVW is the right-hand system. Then come to very concrete number. We had 100,010 has to be 001. 0101001 has to be 100. 00110 has to be 010. See, that's 3 vector. 3 the very fundamental vector, right?
Mm-hmm.
We can also make this as the definition, then extend linearly, you know, saying what the add up, whatever, anyway. It has the UV and the VU get to different direction because of the right-hand system, right?
Mm-hmm.
Then that's it about that. Actually, the most important thing, you not only knowing what that means, you also have to know what that vector really is using x1, y1, z1, xy, z2, z2. Then get a new vector. The first component is y1, z2 minus y2, z1. Then blah, blah, blah. Right? Okay. Then the next thing is called the determinant. The 2 by 2 determinant are always defined to be that way.
Mm-hmm.
Then actually the high dimension, the determinant defined by the lower dimension. So every A1 the upcast AIJ here, like saying AIJ here, A11, the A12, whatever it is. Let's see what you're sharing. It's okay. So those things are called called minors. Okay, that's the name, whatever it is.
Mm-hmm.
Okay, so because it's just a little bit smaller than let me close that. Okay, let's keep coming out. No, okay. So yeah, for example, 3 by 3, then you can use in 2 by 2, calculate it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That one is going to be equal to that. So that's all the definition.
Mm-hmm.
Then I already talked about last time the 3 basic row operation. Before that theorem is easily proved by the induction. We're not going to prove it here.
Okay.
Just remember the determine A times B equals to determine A times determine B. It's very tedious in the program. So the row operation is essentially left multiplication. So the first kind of row operation is switch 2 rows. Switch 2 rows, because switch 2 rows, you get that determinant. A determinant that has has the determinant -1. So it's easy to say actually. So maybe we should say give it a little bit sense about it. So for example, 2 by 2. So change the first row and the second row is going to be 1 here, 1 here, right? So this is the E12 anyway. So have 0, 1, 1, 0. So according to the definition, is 0 minus 1 is -1. So 3 by 3. Let's say E12. Then it's going to be 0, 1, 0, 1, 0, 0, 0, 0, 1. Right?
Okay.
So you calculate, get 0, 0, 0, 0, then get only one of them is working there. So here only one of them is here. So it's that direction. So it's -1. Right? So the one more E13, E23 or E13, you get at 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay, that one even easy. So only one of them in that direction. So you have so only have one in that direction, so it's -1. Okay, so Eij always has determinant. You can sometimes write that way. Most time I can write that way. 1 anyway. -1 answer. Okay?
Okay.
So if B is obtained by switch the 2 rows of A, then you get the determinant has the negative side. For example, you don't really need to calculate it. You can say 3, 4, 1, 2 must be equal to 1, 2, 3, 4. So to say it's really true, you see 3 times 2 is 6 minus 4. So that one is 1 minus 4 minus 6. So, right? So this is true. Then interesting thing, if you have the 2 rows the same, to change those 2 rows will not change the. So for example, I have 1, 2. Then you have another row also called 1, 2. Then you switch them, you get the negative 1, 2. Then how is that? Oh, very interesting. How is this control not doing anything like that? Anyway. That's very funny. Anyway, I just put that 1, 2 there. So you see this one is stem whatever, so got to be 0, okay? This number got to be 0, so a equal to minus a has to be 0, okay? Right? Okay, that's all simple. If you have a 1 row, yeah, this is the obvious thing. We already talked about last time. See, next one is about the e k times the ith row, then plus to the j. That one has a determinant 1, actually, because there is up. I didn't really talk about it. It's up, right triangle. So determine, say, you have 1, 1, 1, 0 before, then you add 1, you have, for example, this is the E1, 3. This thing is up triangle, so I have 0 here, 0 here, 0 here, 0 here, 0 here. So only this row get only this diagonal. Oh, yeah, better. Only this diagonal give you the value. The other diagonal give you value, so got to be 1, right? Okay, so that means if ek times I plus j times a equals to b, then you get determine a going to be equals to determine b, right? Because that one equals 1, and also that one is very important. So we have that thing. I have to keep using that thing. It's very important. Okay, so if you have 1 row as a multiple of another row, then you can always produce a 0. For example, I'll give you, say, 1, 2, then have 4, then 8. So your first row, then you say, let's doing like first row, doing E1 times minus 4 plus to the 2. So first row times minus 4, then to the 2, then it's not equal, then you get 1, 2, then 0, 0. Right? So this is, if you say this is A, this is B, then E times A equals to B. Right? Row operation. Okay? I believe it. Minus. So the original is 1, 1. So first row times minus 4, then that's 1 times 1, 2, 4, 8. Let's see. 22 and 8. You got that one times that one, you got 1. That one times that one, you got 0. See? Right? So this is true, okay?
What if it's like -3?
Then minus 3 you get 1, 2, 1, 2. Then so the purpose for now is produce 0, 0 here. So you got 1, 2, 1, 2. Is that right? So 1, yeah. But still, yeah. You can still send 0 because you know about it, right? So like this, your first row. So what kind of row operation you are going to use to produce one row with all zeros?
The minus 2 times 1 plus 3.
Excellent. There's another one is any row you multiply by a constant. It's called this one because essentially, so what is this? This one is just like one, like for example, k equals 5, then it's just 5, 1. Okay, so this matrix is E5 times the second row, right? The 3 by 3 matrix. So 3 by 3 can say a lot of things already. Anyway. So it's easy to see that matrix has the 5 as the determinant, right? Rest of them just a 0. So the elementary matrices are all easy. So if one row is multiplied by another row, you can also send the determinant as 0 because you can produce the two rows then. If you have one row is multiplied and then, okay, yeah. That's all obviously. Okay, pick up. View.
Okay, done.
Okay, so 3 different elementary matrix. Let's see why do we need to learn those kind of thing at all. For example, we want to calculate the determinant of that thing. Okay, 1 1 1 1 1 1 1 2 1 1 2 2 1 2 2 2, right? So you can use the definition. It's not that much. It's only 24 terms. 24. But it's going to factorial. If you have like 10 by 10, and it's going to be a lot. It's going to be 10 factorial.
Okay.
So we're using the row operation. The first row times minus 1, add to the second row, add to the third row, add to the last row.
Okay.
Right? This will not change the determinant. So the values to be the same thing. So the second matrix, you already feel is much better to calculate, right? So many zeros. Okay. Now I'm going to switch the second row and the last row. Just to switch them. Okay, become like that now, right?
Okay.
Actually, this is already 1, by the way. This is the up triangle. Up triangle is always the diagonal multiple together because you can keep it's easy to see. But anyway, let's move forward. Then I'm using the last row multiplied by minus 1, then add up back to the second row, add up to the second to the first. Then keep add. Actually, this is the 2 steps. Then it becomes 1 0 1 1 0 0 1 0 1. Okay. So the original matrix is going to have the determinant to be what is it?
What? 1?
It's going to be 1. This one, eventually we get 1 0. Oh, sorry. Yeah. Why is that Control Z didn't really work? It's so weird. We got 1, 1, 1, 1. That's the final. So what we did is, so first of all, we're using a bunch of E1, E minus 1 something. Anyway, E, it's not enough. So E 1 times minus 1 times 1 times 1 plus to the 2, then another E blah blah, another E blah blah, 3 of them. So E times minus 1 times 1 plus 3 plus 4. So for that one, we get switch the first and the second. So switch to E, switch 2 and 4. But we what kind of? I think it's E to 4. That's all. There's no parentheses. Don't need that because it's clear, right?
Mm-hmm.
So the last one we use a bunch of. Let's give a name. The first kind of is switch the 2 rows. The second kind of first kind of is switch 2 rows. Okay, second kind of is add 1 row multiple something add to another row. And third kind of is multiple k. Okay, so we only have the first and the second. So this is will be the second again. Will be switch times something the first. So second. That's the second again. I keep kind of. That's the second kind of. This is all second kind of. Second kind of will not give you anything about. So this will give you produce the matrix. We have to determine 1, 1. So this one is going to be minus 1. So you have like a bunch of matrix. Some of them only one has minus 1. So we should have 1, 1, 1, 1, 1, 1, 1, 2, 1, 2, 2, 1, 2, 2, 2. Should have minus 1. Right?
Mm-hmm.
Okay, let's do in a little bit exercise with that you calculate like 1, 1, 1, 1, 1, 1, 1, 3, 1, 1, 3, 3, 3, 1, 3, 3, 3. Just doing a calculation to see what you have. Erase is too small. Too small. Right there. You still remember that one? 1, 1, 1, 3. All right.
Yeah. Wrote it down.
Already done. Got about it. That's too quick. My God. Okay.
It's just 0, 0, 0, 0, 0, 0, 0.
What? Just 0? So you got 0 at the end?
Yeah.
No, cannot be true. Because same thing as what similar to that thing, right? Maybe you look differently. Okay, same idea, same trick. Kind of get 0, 0, 0, 0. Right. So yeah.
Okay, 2 times 2 times 2 times 2. Times -1.
So what is the final result is?
-2 to the 5.
Oh, yeah, this is probably. Let's see. Do I have that one as exercise? Oh, okay. So same thing. You get 1 1 1 1. So 1 1. Oh, sorry. 0 0 0 2 0 0 2 2 0 2 2 2. Right?
Mm-hmm.
And it's very similar to the previous one. So you can actually get 2 out. You like? Can get 2 to 2 to the 3. So 2 to the 3 times 1 1 1 1 0 0 0 1 0 0 1 1 0 1 1 1. Then you can switch the second and the same thing actually. So to the 2 to the 3 times 1 1 1 1 1 0 1 1 1 0 0 1 1. Okay, so the last one is the 1. So you get 32.
Mm-hmm.
How could you get 32?
Well, I did times the first row by 2. And then, is that supposed to be 1/2 and not 2? If you times the first row by 2, does that make the determinant?
Yes, 1/2. Yeah.
Oh, okay.
Yeah, because this is called determinant EK times I. It's only K only. Third kind of matrix. It's not K times K times K times K. It's K only.
Okay.
Right? So this is the third kind of matrix. Third, yeah, the first line. K times 1 row, no matter how many, what the dimension in the matrix is, it only give you 1 K. That's all. Right?
Okay.
On to let's move on. Do you already get it?
Mm-hmm.
Okay, so the next trick. So this is the trick to calculate the determinant. Okay, so if you very high dimension determinant, using this is much efficient. So next thing we can use in the same trick to calculate the inverse. Did we talk about the inverse?
No.
Okay, let's say inverse first. So what is the inverse? So this is actually totally newer to you for the multiplication. So so you can define let's only talking about n by n matrix now. Okay, so every matrix we're talking about in the following will be n by n. So then you can, for A is n by n, then B is n by n. You can define A times B. This is not cross product. It's just the definition we are just used. Okay. The difference. Yeah, usually write as A times B. That's all. So it's another matrix. It's another n by n matrix. Okay. This notation is really bad. So yeah, whatever it is, just A times B. You know what I mean, right? So let's just say 1 by 1, the 1, 2, 3, 4, then 5, 6, 7, 8. This is the two matrix. Then you multiply together, you get another matrix. This is 5, 19 something anyway. So you know what that is, right? Special matrix usually called E or sometimes called I, whatever, equals to 1, 1, 1. Everything anywhere else is 0. Okay? So for example, 1, 0, 0, 1. This is a 2 by 2 identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is 3 by 3 identity. So all elements, you can same thing 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? You know, sometimes we using the thing called I, sometimes called E. Probably most often is called I actually. I think most often called I because of called identity like 1. Okay, like 1 in the general the multiplication where with the numbers. So the thing is that thing is A times I equals A. No matter what it is, I times A always equal A. No matter what the A is.
Okay.
You get that? For example, 1, 2, 3, 4 times 1, 0, 0, 1, which is so 1. Then here, then get 1, then 1 get 2, and get 3, and get 4. Okay?
Okay.
1, 0, 0, 1, 1, 2, 3, 4. So easily you can see it 1, 2, 3, 4. So for every matrix, it's like that. So this is why it's called identity. Just like one in the usual the multiplication. Oh, when the operation equals the multiplication, the 1 with 1 times 5 equals 5. 5 times 1. That's right.
Okay.
So another kind of identity in addition is 0. So 0 in addition is playing the same role. So what that means is 0 plus 5 is a 5. Is 5 plus 0. See, very similar to them. So you see, for example, give this example, say 0. This is the multiplication. This come to the operation in 5, and right? Same thing. 5 plus 0 is that thing. Anyway, right? Okay, this is called for example, when you solve the equation, like saying 5x equals 2. So how do you do it? You x equals 5 inverse times 2, right? So you need to know the inverse. The same thing is with the matrix. For example, 1, 2, I have 1, 2, let's say 2, 3, make it easy. That same times something called x1, x2 equals 5, 6. So you can solve one by one. But if I know some matrix, like say, if I know B satisfies 1, 2, 2, 3, I time B there, okay, then equals to 1. Then I will be very easily find x1, x2 is going to be times 5, 6. Okay, so let me just find the inverse of that matrix for now. Then we come back to what that means. Okay.
Okay.
1, 2, 2, 3. We want to operate row operation. Let me just put something in there. You don't really need to understand for this moment. Just be with me. So I do the first row times -2 added to the second row. Okay, so 1, 2, 1, 0, no change. Then get 0 here, then get -1 here, then get times -2, then get -2 here, then get 1 here. Then I second row times -1, get 1, 2, 1, 0, 0, 1, 2, -1. Then I second row times -2, then add up, then get 1, 0, -2. What? -2? I did something wrong somewhere. Did I?
No.
Huh? Maybe. Okay, -2, then get -4 here. There, no, -2, get -4, then get, oh, okay, then get 2 here. Get 2 here? Oh, I'm sorry. -2, then get -3 here. -2, then add to the get -3 here, okay? You got it?
Mm-hmm.
So that got 0, got 1, got 2, got -1. Okay, I'm going to tell you is, you don't need to understand for now. I'm going to tell you I can take B as this part. So -3, 2, 2, 1. Let's see it's correct or not. So that B times 1, 2, 2, 3 going to be -3, 2, 2, 1, 1, 2, 2, 3. Going to be -3, then got 1 here. Then one got 0 here. Then we got there. Oh, -1. I'm sorry. Okay, you see it? -1, right? So -1 here, then get 0 here. So -1 here, get 1 here. So B is what we want, okay? So if that way, then we got x1, x2 is going to be B -3, 2, 2, -1, and 5, 6. It's going to be the solution. So let's multiply, get -15 plus 12, which is -3. So 10 minus 6 is going to be 4. So you can solve that equation easily by using that similar concept. And the solution is x1 is -3, 2 is 4. You can also write the original equation like this. Okay, so x1 plus 2x2 plus 5, 2x1 plus 3x2 plus 6. This one has the solution. That's the solution. Okay, the idea is you want to find something okay, now let's go to the definition. We'll be back now. Be back into that screen again. So the definition. I should have for a matrix A. Yeah, we usually talking about n by n. So this is the if there is a matrix B such that BA equals to I, then we call B the inverse of A. Here using the word the inverse means the inverse is unique. So okay, you have the following thing, you have to prove it. Okay, so first thing is if B1, if BA equals to I, then AB equals to I. Okay? So the proof actually is a very, have to be using that, here's the proof. We can write, actually, every matrix you can use in the rule operation. So, okay, so first step is if BA equals to I, then determinant A is not 0. Okay?
Okay.
Because of that. Right? Cannot be 0. Right? Okay?
Mm.
The second step, if a matrix A satisfies determine A is not 0, then A can always be written as E1, E2, then E to the something. E1, E2 is all elementary matrix. You understand what happened? So what happened is you can start with A, then just do row operation. Use the first row, then first column some of them must be non-zero. Okay.
Mm-hmm.
Then you put the first non-zero could be the corner over here. Okay. Right.
Mm-hmm.
Then you just multiply whatever the things add up together, you get 0, 0 over there. Okay?
Mm-hmm.
Then you get something else. Then you keep going with this matrix, same thing. Then keep going, you get something like that. Then you get 0 here. Right?
Mm-hmm.
So none of them in the diagonal can be 0 because determinant A is not 0. Then you for the last row, you multiply something, add up back, then you get 0 here, then you get 0 here. Then you keep at the second the backward second row back, then you eventually get something 0, something 0, then only in diagonal has something. Then you just using the third kind of elementary matrix, then you get 1, then must be 1. Right?
Uh-huh.
So which means when every matrix you just multiply elementary matrix, you eventually get identity.
Mm-hmm.
Okay, now let's prove if B sorry, what is that? Huh. So now prove saying if B equals to A, or if BA equals to I, then AB equals to I. Let's prove it, okay? How do you prove it? Because of determinant B is not 0, you get B, it's going to be equal to E1 times E2 times something e to the m for some n. Then you get E1 times E2 times EM MA equals to I. So every EI you have explicitly like saying the inverse, okay? For example, the first kind of EIJ times EIJ is 1. Okay?
Okay.
The second kind of EK times I then plus J will times E then times K times minus K then times I then plus J is 1. The second kind of EK times I and with E the minus 1 over K then times I is 1. Okay, there's 3 kind of things, so which means you can write A equals to, let's call that inverse, which you can write as E1 inverse, E2 inverse. Because E1 inverse, E2 inverse make all sense already, okay? So every elementary matrix you talk about the inverse already makes sense. So in other words, we already know that one is true if A is the elementary matrix. So A is like that, then you just times B again. So A times B again, and B is equal to A times E1, E2, EM. Then you get B, then A times B, A times B, A already have that, so you get EM inverse times E1 inverse times E1 times E2 times EM. So you get here. Here is the 1. So you get EM inverse and E2 inverse times E2 times EM. So eventually you get EM inverse times EM. So you get 1. Okay? So if BA equals to 1, then AB equals to 1. Got it?
Okay.
That's actually proof is very beautiful. Using elementary matrix. Got it? Okay. The next thing is unique. Saying now if B1 times A equals to I, B2 times A equals to I, then we get B1 equals to I times B1. But I is B1A, you can send B2A times B1. One thing I didn't really tell you is I'm going to B2. So one thing I didn't really tell you is the matrix multiplication satisfying the following thing. So this can be proved just by the definition. It's called association. Associativity, whatever, association law. Okay? So that one we're using association law now. So B times A1 then get B2 times I, then get I. So B1 equals to B2. You see? You get it?
Okay.
Previously, weird. Saying if B1 times I equal I, B2 times I equal I, then B1 equals to B2, just because of this. So B1 is B1 times I. Then you substitute I by I equal B2 times A. Then you associate A and B1 again. Then you get B2 times A times B1. A times B1, we know that. We already proved it, is I. Okay? Right? Then you get equal B2. Okay, this is pretty, could be lost. Are you lost?
Well, it's kind of,
So here's the statement. The statement is saying if B1A equal I, B2A equal I, then B1 equals to B2. Okay, this is something we need to prove.
okay.
So the proof goes like this. Why? Because B1 equal I times B1. Then you replace I by B2A, then get B2 times A times B1. Then B8 times B1 is I again, so you get B2 times I, so get B2. B1 equals to B2, that's all. So it has one unique inverse. Okay?
Okay.
How do we, now it's a unique inverse, how do we find the inverse now? So let's back to this example. So how do we find the inverse of this matrix? 1, 2, 2, 3. Okay, this is the RA. How do we find it? Then we doing the following thing. We put A and the I together. You see, right? So we do row operation. So the first row operation we change the E1. Then we get two matrix again, E1A, right? Then you put the E1I. They still together, right? This is the E1I, this is the E1A, right? E1 just the switch, just the first. So now keep going. Then you put E2 here. Then you get E2, U1A. Then you get E2, U1I. Then you keep going, you get E3 here. So you get E3, E2, U1, A. Then you get E3, E2, U1, I. Right? But that thing is I already. Right?
Okay.
So that one we call it the B. The B essentially is an E3, E2, E1. So what you see here is the very important observation is here. So here you have E3 times E2 times E1 times A equals to I, which means if you have, that is better. So if you have the B here, so B here, okay, B here, then B times A is I already. So which means this is your inverse. This is the inverse. Okay.
Okay.
This is a pretty tricky thing. Okay, very tricky. Okay, let's see the example here. So we want to calculate the inverse of 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 2, 2, 1, 2, 2, 2. We want to calculate the inverse. we doing the same thing as before. We put add the first row multiply -1 to the second, to the third, to the last. Then we get this change, right?
Okay.
We just did that in the previous page. Remember? Now we're doing the same thing. Because we're interested in get 1 1 1 1 there. Get 1 0, get ID. Identity. So then you switch the second row and the first row. That become like that. See the 1 here, see 1 here, 1 here. I'm sorry, 1 here, 1 here. The 1 is here, then 1 is here, right? Okay, now the last row multiply -1 at the back. At the back, then you add the back, get like that. Then at the back, the third row time -1 back, then get this. Then add the second row time -1, then at the back, you get like this. So you get the final matrix is 2 0 0 -1 0 0 -1 1. That will be the inverse of the original matrix. So we got the inverse. The inverse you can write as this way, just like exponent. So inverse of that then equal to that. If you don't believe it, verify it. It's going to be true. Okay?
Okay.
Maybe let's doing an exercise. Okay, let's doing one exercise with it. I think you knowing this kind of trick is very, very looks like this kind of thing are also stuck. Crazy. This has like 16 gig memory. This computer still crazy. So let's doing that 1 1 1 1 1 1 1 3 1 1 3 3 1 3 3 3. Calculate the inverse. Okay. I'll be back in several seconds. Let's take a couple of minutes break. All right.
Okay.
All right. How about it? A couple minutes break.
Okay.
All right. Yeah. Okay, you get this one.
Okay.
Okay. So what do you have?
1, 0, 0, minus 1/2. 0, 0, minus 1/2, 1/2. 1/2, minus 1/2, 1/2, 0. Minus 1/2, 1/2, 0, 0.
Oh. Okay, let's check a little bit to see. First one, good. I just randomly check several. This one, oh, good. This one, this one, I think is right. Okay, good. So that thing is really hard to forget actually. As long as you're doing once, pretty hard to forget. Right? Feel good about it? Also, I already show you the example of solve a linear equation, right? So the key is to find the inverse. So for example, you solve this equation, x1, x2, x3, x4, x1, x2 plus x3, 2x4, then whatever. So the matrix, the half is like that. You can write that one in the matrix form like that. Are you good about it? You see?
Okay.
So if we know the inverse already, so then just get the inverse. That's it. See, this is pretty beautiful. Anyway, this example is not that hard. Also, one thing I just remind the inverse. There is a formula to calculate it. It's called I think it's called Cramer formula. That's been so long. I think that's his name. So actually, you have essentially that's using the determinant to calculate. We might mention it next time because it just came to my mind. The inverse has the following relationship. So AB's inverse is equal to B inverse A inverse. AB inverse, okay? So it's going to be because if that thing times B inverse, A inverse, okay, so it's not that way saying, okay? Let's say another way. So always have a little challenge. AB inverse equals to B inverse, A inverse. So the order is important. B is in front of A now. Okay?
Okay.
So why? Because AB, that thing multiple B inverse, A inverse, is going to be association. It's going to be AA inverse and be I. So this is why the AB inverse is going to be. Okay?
Okay.
Actually, matrix is a very, very complicated topic. There's another thing called transpose of matrix. So what that means, switch the rows and the columns. Let me show you what that means. So, for example, 1, 2, 3, 4. So the transpose, usually using the prime. Some book using T. In the future, it probably say should there is a prime or should there T. So just change 1, 2 here, then 3, 4 here. Essentially switch the row and the column. So originally is a row there, now become a column here. The row here, that become column here.
Okay.
Also is a column here, become row there. That's just so any matrix, if you T once, then T another time, is going to itself. Okay?
Okay.
Also, you have AB multiplied together T is going to be BT, AT. This has to be proved by the induction. Unfortunately, it's not that. Actually, there are better proof with it. Using the called quadratic form something. Whenever probably we don't learn it anyway. Also the rank. Did I tell you the rank about matrix?
No.
No. Okay. A matrix can have a rank. And how do you define the rank? Here's the way to define the rank. The matrix A, you just keep doing the row operation. So eventually you can get the one something 0, something 1, something 0, something like that. Could be 0 at the end, whatever. So essentially the rank of that matrix is you count how many ones in there. Let's give you an example. Like saying 1, 2, 3, 2, 3, 4. Then have 3, 5, 7. That matrix. Let's doing the row operation, okay? Then you doing like -1, 1, 2, 3 is still there. Minus first row time -2, then get 0. And -1, get -2, right?
Mm-hmm.
First row time -3, you get 0. You get -1 again, -2 again, right?
Mm-hmm.
So the second row time -1, add to the 0, 0, 0. You can multiply minus 1 if you like. You don't really have to actually. Let's just check the definition back. So once you get up triangle, it's called up triangle. So which means everything is 0. Everything in the bottom is 0. As long as you get the up triangle, you just count how many rows is in there. So 1, 2. So the rank of this matrix is 2. Okay.
Okay.
So so if rank of A or n by n matrix is less than n, then determinant of A is 0. Okay, in other words, if determinant of A is not 0, then rank of A equals to n.
Oh, that's obvious.
Okay, so yeah, only n by n matrix we actually it's not really true. So you can talk rank about any matrix, but the determinant is only the n by n. Okay, it's another thing. For example, this matrix has a rank 3. Actually, this thing is not exactly true though. I have to change this. I have to change the slide. It's not exactly true. You can, yeah, it's not always you can get. Up triangle is good. So if A has the rank n, then A times x equal B has a unique solution because they has the inverse. So this has the same thing if and only if. What happened here? Something happened. Here we go. So this is also if and only if A has the inverse. Okay, so it's for rank if and only if the determinant is not 0, if and only if the rank has that has the inverse. You get it?
Mm-hmm.
So that's all. That's all for the textbook. Actually, we don't have anything. So basically, I didn't follow the order of the book. If you have a second to do at home, then reread the book again to see if you can connect the things in the book and what I talked about. Should be the same thing, but so might be used in different language. Okay. So next thing, let's see. I think we still have. We work together with. I think I just added the thing. Work together with exercise. Let me close this. It's always weird recently because it's pick up the wrong one somehow. Okay. So I'm not sure how many problems you did.
I did number 165 and 170. But 170 I did the long way.
Let me see. All right, that's good. Anyway, let's start with whatever you did right now. So which one? 170. You did a long way. That's good. You have the experience with it. So before 170, What else did you say?
165.
165, the value of A if blah, blah, blah. So probably it's also doing the long way, right?
Uh-huh.
Okay, so let's start with the first one, 164. If A is a 2 by 2 matrix, whose inch is at the first 4 prime, what is the largest possible value of determinant A? Oh, yeah, you figure out.
That's obvious. Let me see. 29. 29.
29, let's see. Let's work together.
Because the 5 and the 7 has to be on the biggest. Like
yeah. 5 and 7?
Yeah.
So first 4 prime are?
2, 3, 5, 7.
Good, that's right. Okay. So 5, 7 has to be like that. 2 and 3 has to be like. Okay. I agree with you. So the next one, calculate that value, right?
Okay.
So you want to work together or want to redo it using the things we just learned?
Redo it.
Wait. You know, actually, it's good. You did the long way, then you have the new way. You can either can have like a feeling saying, "Oh, this is better." I'm also doing together. Doing by myself is going to be equals to
Well, I got enough zeros, but so it should be 1 times 3 times 2 times minus 3.
Okay, let me write 1 times 3. Huh?
So it's minus 18 and then minus.
All right. Well, so what is the number, the eventual number?
36 times 6 minus 18.
Okay, give me the number. Oops.
198. I got the same answer before. So.
Oh, okay, that's good. So either way, I'm in the middle of doing it, actually, you see. If you get the same answer as before, it must be right, okay?
Because that's probably not zeros already. Is it
Yeah,
zeros
okay.
already?
Okay. Yeah. Yeah, you see, I can do in that part, then that part, then I can still switch 1 there, 1 6, then -2, then 4, 1, 4 minus 1, 18, then -1, 9, then 1, -15. I can go to then 1, 6, -12, and can do 4, then 4. Right?
Mm-hmm.
6. Then type 9, oh my God. 55. So you have 5 in the middle. You don't have 5. How could I have 5? It's 5. Is there no right? So you don't have 5 there? I have 5 at the end. 5 times something.
Maybe if you do minus, then it'll be the same number.
Okay, let's continue to see what happened anyway. So you get type 9, so get 108. 108. You get 133. Oh no. Oh sorry. 108, 123. Right? That one. We eventually get 25 times 133 minus 55 times 6. 123 again. So you get 5 times 3 times 5 times 21. No, I'm sorry. 41. 41 minus 11 times 22. Right? So then next 242. 242. That's 7. 3, 33. So 5 times 3 times 33. So probably plus or minus. Let's see the plus or minus thing. Let's go this one. Minus. So totally it's plus. So the end result is plus. Okay.
Okay.
So you have 198. Let's see together what's wrong with it. Okay. So what I'm doing here is I using the second row. Okay, add to the first row. First off, I want to make a 1 here. Okay.
Okay.
I get a 1 here. Then the first row, I multiply 3 to the second row and get like this. So 2 by 3 is 6. 6 then get 4. -1. I might be wrong, okay? It's just a number. But I'm so -3.
Oh yeah, last row.
Is it wrong?
Wait. Oh no, that's right.
Times 3, you get -1, right? 3, you get 18. So everything seems to be right to me.
Yeah.
Then the first one, you type -2, then you get this row. Then type -3, you get this row. Okay? So I actually, based on you only need to calculate that thing. Okay, so don't really, you can be lazy. Yeah, you don't, the other just, so I switch again. Switch the 1 and the 4 and get this. So the first row I mark -4. This then add to the second. And first row mark 9, add to the last. Then get this. So this is a negative thing. So you get a negative, you get a plus. So eventually you should get 5, 5, 5. So what did you do wrong with it?
Oh.
Hmm? How did you do it? Did you, yeah, you can, you know, if you can produce the 1 somewhere, you can produce the 1 and make it easier. That's the way it is. Otherwise, the minus, yeah, fraction easy to get wrong. The next, can we go forward to the next? So let's say there be no inverse. Still saying calculate the determinant. Determinant is 0. There be no inverse. You want to work on that right now? Still using the first row time -2 at the second row. The first row time -3 to the last row. That thing. Yeah, you can calculate it. It has 6 terms. That's not worth it. Oh.
The determinant has to be 0, right?
Yeah.
So,
Right. Yeah. I got it. So
yeah, looks like I got it wrong.
again.
Yeah. Well, I got the same thing as you for the -9, 7 minus 2c,
Mm-hmm.
14, 11 minus 3c.
Yeah. Also, there is a trick. When you get that, the determinant is given by those four number now. The rest doesn't really matter anymore.
Okay.
4 and C do not provide any. So only this one now. So that one, I remove the -1 for the first column because I only care about the 0.
Okay.
Right.
Okay, that's good.
The 167 is really nothing. I don't really see you need any trick at all. Okay. I just give you one more practice with it.
Do
167.
I need to do the
Don't need to do anything actually.
2 minus 6? So -4 times 28 times 5.
140.
Yeah.
Yeah, probably right. So just to calculate determine A, determine B, determine C. That's all. Using the properties that thing. Using that's what you are using.
Mm-hmm.
Okay.
Mm-hmm.
Okay. That one. That's one. You also doing the same thing though. I would put the last row determinant anyway. Minus probably doesn't really matter too much. The first row and the last row switch or whatever. Which I want to put 1 in there anyway. Okay.
Mm-hmm.
Then you give you one more chance.
Okay.
Okay, I will give you several minutes to do. Yeah, not too many left actually. Not too many left. Probably we can finish today.
Okay. I got the 3x3 one, and there's a bunch of zeros, so.
Okay, so what's the end result?
Negative a squared times a minus 1 squared.
That's it?
Minus a minus 1 to the third. Okay.
Okay, let me see. What do you have again? So, can you say one more time?
It's negative.
I think say a minus 1 square minus a minus 1 something, right?
Okay, let me write it down.
Okay, you can write down. Okay. Huh. Let me see. Oh, you're there?
Uh-huh.
Huh. What I see? What I see it? Oh, okay, I see it. That's interesting. It's my screen. Huh.
Okay. Negative a minus 1 to the and times a squared plus a minus 1.
That's it?
Uh-huh.
Interesting, actually. You still see the, oops. Hold on, I stopped it. Oh, okay, so you have a minus 1 square, a square plus a minus 1.
Uh-huh. Negative.
So here is negative.
No, the whole thing is negative.
Oh, okay. Okay. Let's see, want to verify. I feel it's kind of weird. So equal negative. I want to put a 1 somewhere. 1, 1, 1, a 1, 1, 1. Then equals negative 1, 1, 1, a. Then minus a get there. 0 here. 1 minus a square. A minus 1, 0. A minus 1, 0, 0. 0, 0, a minus 1, 0, right?
Mm-hmm.
So only that part now matter. Only this part matter now. So everyone has a minus, so I have minus times 1 minus a times a minus 1 times a minus 1. Then got to essentially got 1, 1, 1 plus A, 1, 0. Wow, bunch of 0 already. 0, 1, 0. Yeah, if I switch, I don't really need to. It's already a lot of 0. Yeah, switch. I switch the first, then the one, then switch again. So, okay, so one step at a time. Okay, here's A minus 1 to the cubic already. You switch it, then get 1, 0, 0, 1, 1, 1 plus A, then 0, 1, 0, get minus again here. Again, so I switch again, the first, second, the last to get 1 cubic, so 1, 0, 0, 0, 1, 0, 1, 1, 1 plus A. So I add first row multiplied by minus 1, add to the last row and get 0 here. Nothing changes there. So the second row minus 1 get 0 here. Wait. All right. Let's see what's wrong with it. So first row minus 1 or minus A. That one. Oh, here I'm missing something here. Missing something here. All right. Do you see it? Actually, it's backward. Let me see, it's backward actually. Right?
Okay.
Do you see it? So actually, we have minus 1 here. Oh, this one has something. 拎进去先。Huh? Here we go. Minus 1 here, right?
Mm-hmm.
So the switch doesn't really make too much sense anymore. Switch. Then here's the right. So the first row add up, then get A plus 2, then get A plus 3. 1, 0, minus 1, minus 1 here. So the eventual result is, okay. Yeah, that makes sense, okay. Why it makes sense? Because first of all, if you A equals to 1, is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this one is 0, right? So this 0, actually, you can tell this determines it's just to repeat too much. Actually, A equals to 3 0 here. Can you do that? So it's actually one. Rank is 1. The rank is only 1. Okay? So this makes sense as A minus 1 to the 3 times. So you also have 1 equal to the 3. So every thing add up together is going to be 6, 6, 6, 6. You can see it only has a rank of 1, so it determines minus 3. Yeah, minus 3. Okay, minus 3. Every add up together is 0. Add up together is 0, 0, 0. So minus 3. So A equal minus 3 definitely is a 0, right?
Mm-hmm.
So this is why this is right. Okay. It's 169 is pretty straightforward. You just can say what it is. That's all.
What?
169. If wxyz equals 4, then what is the 4? fw4x4y equals z.
Same thing.
Same thing.
Oh no, 16 times 4.
16 times 4, exactly. So 170, let's calculate 170.
Okay. You already did that earlier.
Okay. So, okay, whatever, yeah. What do you get anyway?
Well, before today I got, let's see. $768.
That's probably too much. So using the row operation, you want to practice now or want to practice afterward?
I think we already did it.
Huh? We did. Yeah, we did similar thing, yeah. Yeah, exactly. So anyway, so that answer looks like too big to me. 171. Maybe you doing that quickly?
What's a to the minus 2?
Just a to the inverse to square.
Oh, okay.
So a to the inverse should be very easy. Yeah, you just need to find a to the inverse. That's all. Okay? Then we're done today. So find the inverse. That's all.
Okay.
So using the trick we learned.
Okay, the inverse is 1/2 minus 1 minus 1/2, 2.
Okay. Yeah, looks like good to me. Yeah. Okay. So so the last one could be a little bit hard. I think we talk about next time if you don't figure out. Okay.
Okay.
Probably it's hard to understand what I really mean in the beginning. So that one you probably need to re-verify it to see what the answer is.
Okay.
That's all for today. You don't really have too much homework. Actually, we're doing something with a complex number. I will send a set 10 problem to your mom.
Okay.
Then you can take a look to see how many we can do. Okay? Okay, thank you. Bye.